Hello! In today's lesson we are going to look at tectonic plates, and by the end of this video lesson you will be able to explain that the Earth's crust is split up into different tectonic plates, explain how convection currents move tectonic plates, and describe and explain the differences between different plate boundaries. So to start off with, we're just going to recap on our knowledge of the structure of the Earth, because we need to have a good understanding of this to understand some of the concepts in today's lesson. So if you pause the video and answer these quick true or false questions. Okay, hopefully you have now got down whether these statements are true or false. So let's go through the answers. So number one says the Earth's crust is one solid piece of rock. Now this is false, and we know that the Earth's crust is actually split up into different pieces. Number two is the pieces of the Earth's crust are called dinner plates. This is also false. The pieces of the Earth's crust are called tectonic plates, our focus for today's lesson. 3 was the thickest layer of the Earth is the crust. Now this is false. The thickest layer of the Earth is in fact the mantle, and actually the crust is the thinnest layer of the Earth, like the skin of an apple. 4 was the hottest layer of the Earth is the outer core. This is true, and the outer core is approximately 6,000 degrees Celsius, so almost as hot as the sun, which is very, very hot. 5 is the Earth has 5 layers. This is incorrect, it's false. The Earth has 4 layers, and going from the outside in, we have the crust, mantle, outer core, and inner core. And 6 was that in the mantle, hot magma rises towards the crust. This is true, and this is going to be another concept that we are going to focus on today. Okay, so as we've just discussed in the last slide, the crust of the Earth is split up into different pieces called tectonic plates. And these tectonic plates kind of float around on the mantle and they move over time. And so if we look at a map here, we can see the main plates that we have on our Earth. Now, you might be looking at these plates thinking, oh, there are some funny names there, but actually most of the names of the major tectonic plates are linked to what land or ocean is found on them. So let's take, for example, the North American plate. What a surprise, North America is found on the North American plate. Africa is found on the African plate. South America is found on the South American plate. Now, the Pacific plate is unsurprisingly the plate that has the Pacific Ocean on it. There are a couple of plates though that have slightly different or confusing names. For example, the Eurasian plate. Now that just means that Europe and Asia are found on this plate, and so the words Europe and Asia have been combined to make Eurasian. And this is the same for the Indo-Australian plate, where we've got the Indian subcontinent and also some of the Middle East and also Australia on this plate. So we've called it the Indo-Australian plate. Okay, quick activity. Pause the video and try to write down the names of the plates that are labelled. Alrighty, hopefully you have the answers to A to H. Let's go through them then. A is the Eurasian plate, B is the Pacific plate, C is the African plate, D is the Indo-Australian plate, E is the Antarctic plate, F is the North American plate, G is the South American plate, and H is the Nazca plate, the only plate that doesn't really link to the continent or ocean that is found upon it. Alright, so if we go back to this map showing the main tectonic plates, you can see that there are some red arrows found on the map. Now these arrows indicate the direction in which the plates are moving, because our tectonic plates don't just sit statically on top of the mantle, they move very, very slowly. Now they move at a rate of 0.6 centimetres to 10 centimetres a year. So the map that we've got in front of us isn't going to change very much in your lifetime. But over time, these plates do move. And the reason that they move is because of convection currents. Now, last lesson we discussed how in the mantle, the magma that's found there, the molten rock, doesn't just stay still, that moves too. And we can see that happening here in this animation. Let's look at that in a little bit more detail. So here I've frozen the animation so that we can see what happens. Now the outer core, as we've said previously, is very, very hot, almost 6,000 degrees. And that means that any magma found touching or close to the outer core will start to heat up. And because it's a liquid, that magma will then rise. And we can see that here with this vertical arrow. Now, that hot magma rises all the way to the top of the mantle where it meets the crust. And when it meets the crust, that magma can't really, in most places, keep moving upwards. And so it starts to spread out sideways, left and right. And as it does this, it moves left and right underneath the plate. It starts to move the actual plate above it with it because of friction. So these two plates here that we can see are going to move left and right. Remember that this happens very slowly. Now eventually, because this magma has been at the top of the mantle for a long time, far away from the outer core, this magma is going to cool. And because it's a liquid, when it cools, it sinks back down towards the bottom of the mantle. Unsurprisingly, when it hits the bottom of the mantle, it starts to heat up and it will eventually start to rise again. And we can see a cycle now occurring. So this cycle of warming magma, it then moving a plate and then sinking and warming, is called a convection current. And these convection currents move our tectonic plates very slowly across the surface of the mantle. And we know that this happens because of something called continental drift. Over time, scientists have worked out that the continents that we know today did not used to look like this. And very, very slowly, because of convection currents, these continents have moved around on our planet, like we can see in the animation here. Okay, so now we know that the tectonic plates move. We need to think about what happens at the edges of the tectonic plates, because when plates are moving in different directions, they will either move away from each other, towards each other, or past each other. And this gives us different features of the landscape that we need to know about. So here I've highlighted the three directions that our plates can move in, and we're going to look at that in a little bit more detail now. We're going to start off by looking at the plate boundary that occurs where we have our rising magma in the mantle. So here, the magma rises up and draws two plates apart. Now this happens in oceans and in the continents, and we're going to think about it in terms of oceans first. We're going to think about the mid-Atlantic ridge, which is actually two plate boundaries joined together, and they're shown on this map with the yellow circle. So we have the North American plate and the South American plate moving largely westwards, and the Eurasian plate and the African plate moving eastwards. And this forms a big crack, effectively, down the middle of the Atlantic Ocean. So if we look at this animation here, we can see that the two plates are moving eastwards and westwards away from each other. And when this happens, magma is forced up between this crack. Now when the magma reaches the ocean floor, because we're underneath the Atlantic Ocean, it starts to cool and forms rock. It forms new land, which is why this plate boundary is called a constructive plate boundary. So when this magma is being forced up between the plates, we sometimes get earthquakes occurring. We also get volcanoes occurring on this plate boundary because magma is able to rise to the surface of the Earth. And if we look specifically at Iceland, which is found on the northern end of the mid-Atlantic ridge, we will see that there are several volcanoes here. So on the map on the left, we can see some red triangles. These are the volcanoes that we're talking about, such as Katla or Eyjafjallajökull. And Eyjafjallajökull is the volcano that caused the massive stoppages all over the world in 2010 when it had a big ash eruption. The picture on the right shows a picture of the actual mid-Atlantic ridge, and we can see here the two arrows showing the direction that these two plates are moving away from each other. We also sometimes get constructive plate boundaries occurring on continents. For example, the East African Rift Valley, which we're going to look at now. And we can see here in this animation that as the plates move apart, as a continent effectively breaks apart, the land spreads and eventually a sea is going to form in that gap. Now, if we look at the East African Rift Valley, we actually have the African plate splitting into two, forming the Somali plate and the Nubian plate. And the East African Rift Valley is thousands of miles long and has 9 countries in it. For example, Kenya, Uganda, Rwanda, Ethiopia, Malawi and Mozambique. Unsurprisingly, there are volcanoes found along this Rift Valley. Mount Kilimanjaro and Mount Kenya are found, but also Mount Nyiragongo, which is a very active volcano. When convection currents occur, 2 plates are pushed away from each other, and this means that eventually the other end of this plate will meet another tectonic plate. And when this happens, we get what's called a destructive plate boundary occurring, or in American terms, a convergent plate boundary. And this is what we're going to focus on next. At a destructive plate boundary, we have a continental plate and an oceanic plate meeting, and land is destroyed, hence why it's called a destructive plate boundary. So here in the animation, we can see the Eurasian plate, which is a continental plate, and the Pacific plate, an oceanic plate, are colliding. Now, the Pacific plate, because it's oceanic crust, is going to be heavier than the Eurasian plate, or denser. And this means that when these 2 plates meet, the Pacific plate will be forced underneath the Eurasian plate. You can see this with the arrows that are moving. And when this happens, we have the formation of a subduction zone. And here, because 2 plates are being forced past each other, earthquakes occur. Now, subduct means to sink, okay, or go underneath something. And when our Pacific plate subducts underneath the Eurasian plate, the rock of the crust starts to melt. Once it's melted, some of it then forces its way back up through the crust, through the continental crust, to form volcanoes. And we can see this happening on the Eurasian plate. Obviously, because magma is being forced up through rock in the crust, this creates a lot of pressure and we get earthquakes occurring as well. So in Japan, there are lots of volcanoes, and this is the reason why, because Japan is found on a destructive plate boundary. Now, Japan is also quite mountainous, and it's mountainous because as the Pacific plate forces its way underneath the Eurasian plate, some of the Eurasian plate gets kind of caught up and pushed up, as we can see with this purple arrow. Now, this pushing up creates mountains, and we call these mountains fold mountains. So, here we have a little quick activity building on our knowledge of a destructive plate boundary. I've got a diagram of a destructive plate boundary on the slide, and I would like you to pause the video and match up the letters on the slide to the statements that we've got, to the features. Okay, let's check over those answers. So A, you should have oceanic plate, which is number 1. B is number 2. The oceanic crust sinks underneath the less dense continental crust. C is number 3. The oceanic crust melts and rises. D is number 6, which is the mantle. E is number 4, continental crust. And F is number 5, explosive volcanoes. In some parts of the world, we get 2 plates colliding together, but both of them are continental. And when this happens, we get what we call a collision boundary. And an example of a collision boundary is the one found between the Indo-Australian plate and the Eurasian plate. Now, these 2 plates have been slowly moving towards each other for millions of years. And between them, there used to be a sea called the Paleotethys Sea. Now, when that sea started to close up, we had some subduction of oceanic crust, but eventually the sea disappeared completely and we had two continental plates then moving towards each other. And when this happened, we had the plates both folding up, creating the Himalayas. And in some parts of the Himalayas, we will find fossils of sea creatures, remnants of the sea that used to be between the two plates, but over time the rocks were pushed up and are now found in some of the mountains of the Himalayas. The final plate boundary we're going to look at is a conservative plate boundary or a transform plate boundary, and this occurs when we get two plates moving sideways past each other. So the plates can either move sideways past each other going in opposite directions, or they can move past each other in the same direction but at different speeds. And this movement past each other means that friction is going to build up because the sides of our plates are not smooth, they're quite rough. And this means that as the friction builds up, the plates sometimes get stuck. When they get stuck, they still try to move. So pressure builds up and eventually this pressure is released, creating an earthquake. Now, at this type of plate boundary, there is no real land destroyed like a destructive plate boundary, and there is no new land created. And we get no volcanoes at this type of boundary because there's no real gap for magma to get up to the crust from the mantle, and there's no subduction of crust which then melts, providing magma for volcanoes. A real life example of this plate boundary is on the San Andreas Fault, which is found on the western coast of North America. Here we have the Pacific plate and the North American plate both moving northwards, but the Pacific plate moves faster than the North American plate. And so, along this plate boundary, there are many earthquakes that occur. The picture on the right shows what the plate boundary looks like in real life. Okay, we're going to do a quick activity now. So on the slide you will see 3 diagrams showing the movement of plates, and you will see the names of the plate boundaries. I would like you to pause the video and match up the diagram with the correct name of the boundary. Okay, hopefully you've got your answers. So, number 1, a constructive plate boundary matches up with diagram C. The plates are moving away from each other and new land is being constructed. Number 2, a destructive plate boundary matches up with diagrams B. Here we've got plates moving together and the denser oceanic plate sinks underneath the less dense continental plate. And that means that 3, the conservative plate boundary is A, where we have 2 plates sliding past each other. Okay, the final thing for us to consider is the link between plate boundaries, earthquakes and volcanoes. We've discussed that on different plate boundaries we get earthquakes and volcanoes occurring, and now we're going to have a look and see how that matches up. So this map that you've got in front of you right now shows our plate boundaries. And this map now shows where we have volcanoes and earthquakes occurring. And you'll see that actually down the middle of the Atlantic, where we've got the mid-Atlantic ridge, remember our plate boundary between the North American and Eurasian plate and the South American and the African plate, we have loads and loads of earthquakes and some volcanoes. We can see that around the Pacific Ocean, we have something called the Ring of Fire. This is because all around the edge of the Pacific Ocean, we have volcanoes occurring, and so it's considered a fiery ring. And we also have many earthquakes, again matching up with our plate boundaries. Okay, so we've done lots and lots of learning here, and now you're going to use that learning and the information from the video to complete activities 2 to 4 on the activities map that you have. Activity 2, there is a website given called Duxters, and there is a quiz on that website that I would like you to take. You then need to take the tectonic plate quiz and see if you can get 100% naming the different tectonic plates. Activity 3 has a worksheet linked to it, the convection currents worksheet, and you can either choose to complete that worksheet or to create your own detailed label diagram showing how convection currents move plates. Activity 4 is to make a poster about the different types of plate boundaries and to then make a set of mimes to help people remember the movement of plates at the different types of plate boundaries. Good luck!